Hi, welcome back to chapter 11, part 4. And this is the last part of the chapter. We're going to learn about human genetics and pedigree analysis. So, remember how I was talking about how garden peas are such great things to use for experiments? Humans are not great subjects for genetic experiments. Generation time is way too long. And parents, humans, we don't have a lot of babies. So relatively few offspring. Remember the hundreds and hundreds of offspring in the pea plants? Yeah, that doesn't happen with humans. And of course, doing any kind of breeding experiment in humans is completely unethical. But we can still use the principles of Mendelian genetics to figure out human genetics. And we're going to do that using the idea of a pedigree. Now, a lot of people think about pedigrees as something that you use for dogs or maybe horses or things along those lines. But pedigrees are not just for dogs and horses. They're a family tree, and a family tree that focuses particularly on a very specific trait. So a pedigree analysis will only look at specific traits. It does describe that trait of the parent and the children across at least 2 generations, if not more. We'll learn a little bit more about these ones down here. These are X-linked dominant and X-linked recessive. We'll learn about that in the next chapter. But for now, we're just going to try to figure out if something is autosomal dominant or autosomal recessive. And we're going to do that based on pedigrees. Now remember that just because something is dominant doesn't mean it shows up more often. And because something's recessive doesn't necessarily mean it shows up less often. No, when something is dominant, it means if you've got the dominant allele, that's the thing that will show. And you can pass that on, just like you can pass on recessive. But these 2 individuals right here have a kid that does not look like them. That must mean that this kid is recessive. And that must mean that these 2 parents are dominant but heterozygous. On the other hand, these 2 parents are showing dominant, and this one is showing recessive, but it's not showing the trait. This is the trick with pedigrees. The ones that are colored in, that's the trait. The ones that are colored in, that's the trait. So here, same exact pattern, 2 parents that are showing dominant, but the trait, is dominant. Over here, same pattern, right? These 2 parents are dominant, this kid is recessive, but the trait is recessive. So again, depending on how you look at that pedigree, it's going to show you different information. So we can use pedigrees to predict things about the future offspring. Before we move on, I just want to take a step backwards and kind of introduce you briefly to the idea of what's going on here in these pedigrees. So any circles are female and any squares are male. That's the first thing. So male, female. A horizontal line that connects them has traditionally been known as a marriage line. But I want to emphasize to you that doesn't mean they had to be married. It just means that they had to have babies together. So we call it a marriage line, but that's kind of like a remnant of the way we think about traditional families. So marriage line. Anything that goes down from that marriage line is an offspring or sibling line. So everybody that's connected by that line that comes down from the parents are siblings. This one right here is not a sibling because it's not directly connected to those parents. So we could say, either you could say that they married in, or you could just acknowledge that those 2 people had babies together. So anything that's colored in, like you see here for this square, this male individual here, we say that they have the trait. and this female here has the trait, right? The ones that are not colored in lack the trait. They don't have the trait. So, and then just something else that's important here. Sometimes we do see these double lines connecting individuals, and double lines connecting individuals means that closely related individuals are having babies together. So these would be cousins that they're having kids together. Okay. So we can use our multiplication and addition rules to help predict the outcome of specific phenotypes, or you could kind of just like do Punnett squares in your head. That also works pretty well. But the whole point of these pedigrees is not just to like whimsically figure out if if brown hair is dominant or blonde hair is dominant. We usually use pedigrees to figure out if a disease is dominant or recessive. We usually think about this, and actually the very first time this was ever figured out, it was done to figure out how Huntington's disease was passed on. And we'll talk about that again in a little bit. And I mentioned it before already. So that's the basics of how you read a pedigree. And they are powerful. So here we have our mating. There's a male without the trait. There's a male with the trait. Female without, female with. Those are offspring. And they're done in birth order from the oldest to the youngest. And if we look at this pedigree right here, it's already been filled in for us. This is a pedigree for whether or not you have widow's peak. And so here you see this area of the hairline right here that comes to a point. That's the widow's peak. And we do know that widow's peak is dominant. But we could have figured that out just by looking at this pedigree. Because we know, like, here's a male with the trait, and here's a female without. And they have 4 kids. And some of them have the trait and some of them don't. But right here, look at this. Here's 2 people with widow's peak and they have a kid without it. The only way that could happen is if those 2 parents were heterozygous. And that means that they have the trait and that trait must be dominant. That's the only way you can get a recessive. Now, if we look over here, this is a very similar pedigree. In fact, if you look at it, the only difference between this pedigree and this pedigree is which boxes or circles are colored in. Right here in this grandparent line, this first box is colored in, and this one, the box is not colored in. It's the same family that's being analyzed, but they're being analyzed for a different thing, a different characteristic. And in this case, the characteristic is whether or not they can taste a substance called PTC. And PTC, if you can taste PTC, it tastes very bitter, which is why she's making this face right here. She can taste this bitter thing. This person cannot taste it. And all we're interested in is who cannot taste it, right? So we're coloring in the boxes of people who cannot taste it. That's the trait, not being able to taste. So these ones would not be colored in because they can taste it. This one's not colored in because they can taste it. Here's 2 parents that can both taste PTC. They have 1 kid that cannot taste PTC and 1 kid that can. The only way that you can get this to happen is if both of these show dominant and this one shows recessive. So not tasting is recessive, and having widow's peak is dominant. Big W for dominance. We can use pedigrees to help us determine these very things of whether something is dominant or recessive. And so we're going to get some good practice with that in lab, and we'll go through a couple of examples also. But before we do, let's just think about how we can use this, not just to, whimsically decide whether or not widow's peak is dominant or recessive, and the same thing for whether or not you can taste PTC. But we can use it for figuring out genetic disorders. And some of these genetic disorders are quite life-threatening that we're going to be talking about. Some of them are very hard to hear about. So the one that we're looking at right here is the gene for albinism. And you can see these are siblings right here. And one of the siblings has normal melanin and the other sibling does not have melanin being deposited in their skin. We say they're albino, but they're siblings. And so there's this gene for albinism. If you have the dominant allele, you're going to make melanin. If you have the recessive allele, you're not going to make melanin. And it doesn't matter if your other alleles code for really dark skin or medium skin or light skin. If you've got little a, and oh, here's another typo. I'm going to fix that for you right now. Sorry about that. So if you have the little a, that means you'll have albinism. Again, we're going to use this principle to help us understand pedigrees. If a disorder is recessive, then you have to be homozygous recessive in order to have the disorder. We use the word carriers. That's actually an important word for looking at pedigrees. We use the word carriers to describe people who are heterozygous. That means they carry or have the recessive allele, but they don't show in their phenotype. They show as typically normal. Most people who have recessive disorders are born to parents who are carriers of the disorder. Unless there's some weird mutation that happens during development, most of those parents are going to be heterozygous. Here's a pedigree that shows recessive inheritance. And one of the tricks here is that you can see that, one of these parents has the disorder and one doesn't. And they only have one kid, right? That's a marriage line, right? So they only have one kid and that kid doesn't have it. But this couple right here have 1, 2, 3 offspring and one of them has it. So the only way for this couple who does not have it, right, they're not colored in, to have a child who does have it is if it is recessive. So both of these parents here are big A, little a. Big A, little a. That's the only way that you could get this little b to be little a, right? So another way that we can talk about this is we can say that it, and that means the trait, okay? The trait, it, skips a generation. So we see the trait in this generation, and then we follow their kid, it's not in this generation. And if we follow that, it is in this generation. So we say it skips a generation. We can actually see the trait skipping several generations in this pedigree as well. So let's take a look at what that several generations skip. So it is in this generation and is not in this generation, right? We said it was in this generation, but I just mean this couple. If we look here, it's not in this couple, right? But it is in that kid. So we say this skipped 2 generations. It was in there, not there, yes, there. So skipping 2 generations here, but if we follow this path, it only skipped 1 generation. You really, really, really have to think about each individual child in the generation as being a separate event, okay? So most people who have, again, recessive disorders are the offspring of parents who are heterozygous. And that's, again, true for recessive disorders. If a recessive allele causes the disease, if it's rare, then there's more likely a chance for that rare allele to show up within a family. And so if two close relatives marry, like these cousins right here, if these cousins marry, then they both had a chance of inheriting this recessive allele from this parent, from this grandparent, really. So this one would probably be heterozygous, right? And actually, this one would definitely have to be heterozygous because he got one allele from this recessive parent, and this recessive parent only has little a's to give. We don't know if parent one there is big A or little a, so we can kind of like leave a blank there. So we know this one's heterozygous. And we know this one also must be heterozygous. This child right here must also be heterozygous. And they have a chance of passing on that little a to this kid. And it turns out that happened. This kid right here is heterozygous. And this kid right here, and again, they're cousins, is also heterozygous. And if we look at their offspring, look at that. 2 out of the 3 offspring, just by chance, happen to get little a, little a. Again, when people who are closely related have babies together, the chances of those rare alleles showing up are much greater for this reason that I kind of went through right here. We do have a word for that. It's consanguineous. Consanguineous means having babies between close relatives, especially if those close relatives are both carriers. Most societies do have rules. Most cultures do have laws or taboos against marriages between close relatives, but that's not always been the case historically. If you think about like the royal lines of Europe, they actually encouraged you to have mating or marriages within the family so that you could keep the money in the family. That was before we understood really the science behind why you should not have kids with a close relative. So we're going to spend the rest of this lecture talking about some various diseases and look at some of the ways different things are inherited. So cystic fibrosis is probably the most common lethal, that means deadly, genetic disease in the United States. 1 in every 2,500 people of European descent have cystic fibrosis. So cystic fibrosis occurs because the chloride transport channel in the plasma membranes of your cells causes chloride ions to build up outside of the cells. That's why earlier when I talked to you about their skin being salty, that chloride being outside of the cells, it's what you're tasting on the skin is that saltiness. Some major symptoms besides the ones that were already listed include mucus building up in the internal organs and not being able to absorb nutrients very well in the small intestines. And we figured this out through pedigree analysis. Sickle cell disease is also an extremely common disease. This affects about 1 in 400 African Americans, people of African descent. The reason for this is caused by a single substitution in an amino acid in the blood or hemoglobin protein in red blood cells. If you're homozygous, every bit of hemoglobin that you make is abnormal, and it does look sickle-shaped. I've got a picture of this on the next slide for you. Some symptoms of this include physical weakness, pain, organ damage, stroke, and paralysis. This is a very painful and deadly disorder. So, but it's painful and it's deadly, but also has an interesting reason for why it's so common in African Americans. So, if you're heterozygous, which some people say that you have the sickle cell trait, you carry the sickle cell trait is how I prefer to have it said, but some people say you have the trait. Again, I prefer to say carry the trait, or I prefer to say heterozygous. They tend to be very healthy, although there might be some symptoms, and you might only experience those symptoms if the environment that you're in is low in oxygen. For example, if you climb a mountain or in an airplane where you're losing oxygen, or maybe you have COVID, or maybe you've been exercising a lot. So low oxygen. When that happens, part of the hemoglobin fiber protein causes the whole red blood cell to turn into this sickle shape. If you are normal, that means that you could either be heterozygous or normal. But in this case, we're going to look at heterozygous, okay? Half of the hemoglobin that you make is going to be sickle cell, and half of the hemoglobin you make is going to be normal hemoglobin. And so in very low oxygen, some of that hemoglobin is going to be behaving just fine, but the other is going to stick together and form these sickle cell hemoglobin proteins. And what that means is that in very low oxygen, some of your red blood cells are going to turn into the sickle shape, and some of them are going to be normal shape. So heterozygotes are less susceptible to having the feeling badly when it comes to the illness. And here's the weird thing. People who are heterozygous are much, much, much less likely to get malaria. Now, malaria is very common in Africa. It's also common across regions around the equator, but it is common in Africa. And it turns out that there was this mutation in people that lived a long time ago in Africa, and anybody that had this mutation didn't die of malaria. And so they didn't die of malaria, they passed the successful gene on. And as time went by, people started having babies that were homozygous recessive. And that's when sickle cell disease started showing up. We can see that dominant disorders are also able to figure that out if you look at pedigrees. So this is a pedigree that shows a dominant disorder. Now, how do we know it's a dominant disorder? Well, if you look very carefully, you'll see that every generation, follow the path of my red dot here, every generation that has it actually has it. Any generation that doesn't, none of their kids do either. So it's always showing up in a generation, like here and here. If it doesn't skip a generation, then it's dominant. Dominant alleles can cause lethal diseases, but they're rare. Because usually, if it causes a dominant disease that causes death, often that would happen before you could reproduce. So that doesn't really make too much sense. Most dominantly inherited disorders cause death after you reproduce. So you can pass that on to any offspring. And then as you get older and older, it starts to show up. So there's a couple of examples of dominant disorders that I want to go through with you. The first one is achondroplasia. Now, achondroplasia is just a form of dwarfism. It is caused by a dominant allele, and it is rare, but it's not exactly lethal either. It's rare. People with achondroplasia can reproduce. If you have achondroplasia and you're heterozygous, then half of your offspring will also have achondroplasia, approximately. Here's the interesting thing, and I mean, this is also a tragedy. If two people who have achondroplasia have kids, then 1/4 of their offspring could have both dominant alleles, and having both dominant alleles is in fact deadly. That's probably one of the reasons why achondroplasia is so rare. Another example is Huntington's disease. And Huntington's disease is a deadly disease. It causes the nervous system to degenerate. And you don't know that you have Huntington's disease by phenotype. Like I mean, you could get a genetic test these days, but you won't know you've got it until you're somewhere between 35 and 45 years old. And that's when the deterioration starts to begin. There is no treatment for Huntington's disease. It's irreversible and it's fatal. And it often leads to just the deterioration of the brain, and frequently does result in suicide as the cause of death. Remember we talked about multifactorial disorders before, or multifactorial traits before. Remember that has a lot to do with environment. Well, there are disorders, human disorders, that are also multifactorial, including heart disease. You might have a gene for heart disease, but if you're eating a lot of red meat, if you're eating a lot of high animal fat diets, you're more likely to get heart disease. Same thing for diabetes. There is a genetic aspect to it, but if you have a diet high in sugar, then you're more likely to develop diabetes. Cancer, same thing. There are genes that associated with cancer. We're very familiar with the ones that cause breast cancer, but you can get breast cancer also by smoking, and other environmental conditions can cause this. Alcoholism. There are genes that lead people to be more susceptible to alcoholism or less susceptible. But if you are in a very stressful environment, or if you've been exposed to a lot of alcohol in your time, then you're more likely to develop alcoholism. You might have the gene for alcoholism, but if you never drink alcohol, you won't become an alcoholic, if that makes sense. Same thing for mental illnesses. So lifestyle does have a tremendous effect on phenotype for diseases that we think about in humans. If you are suspecting that you might have a genetic disorder or might pass a genetic disorder on to your offspring, you can get genetic counseling. And genetic counselors provide information. It's similar to getting like a 23andMe or an Ancestry.com kind of analysis, but you can actually talk to somebody who is well versed in this information. So that's a good idea if you're worried about it, to get some genetic counseling. Remember that every child that you may have represents an independent event. So just because you have a child that has a genetic disorder doesn't mean your next child is going to have the same genetic disorder. Those are independent events. So kind of keep that in mind, that you're not always going to have children that have that if you've had one that has had a genetic disorder. And also remember that genetic counseling absolutely relies on an understanding of Mendelian inheritance. So lots of practical things in this chapter, and also lots of very interesting math and, of course, genetic crosses. So we'll be practicing those in lab. I hope this will give you a good background to learn your lab this week.